Have you ever watched a drone flying smoothly in the air, moving forward while simultaneously rising upward? That's a perfect example of motion in a plane. When an object moves along a path confined to a plane, which means to dimensions, we describe it as motion in a plane. For example, a football kicked at an angle or a bird flying in a straight path both have components of motion, forward and upward, happening together. To analyze such motion precisely, we use a mathematical tool called vectors. Why? Because vectors allow us to represent quantities that have both magnitude and direction. Let's explore how displacement, velocity, and acceleration work in two dimensions. When a particle moves from one position to another in a plane, the change in its position is given by a displacement vector. This displacement vector is simply delta our vector equals our final minus our initial. Next, velocity is defined as the rate of change of position. In vector form, we express it as v vector equals delta our vector divided by delta t, where t is time. Similarly, acceleration is the rate of change of velocity. So, we say a vector equals delta v vector divided by delta t. Now, here's something interesting. Since direction plays a role, velocity and acceleration vectors can change even when the magnitude stays constant, like in circular motion. Visualize a curve where the velocity vector constantly changes direction. That's where vector algebra becomes essential in analyzing the path. Let's explore how velocity is defined both as an average over time and at an instant. Average velocity is the total displacement divided by the time taken. In two dimensions, it's written as v equals delta r divided by delta t, which breaks down into v equals delta x divided by delta t in the i-hat direction plus delta y divided by delta t in the j-hat direction. Now, to get the instantaneous velocity, that is, the velocity at a precise moment, we take the limit as delta t approaches 0. This gives us the derivative of position with respect to time, v equals dr divided by dt. It's important to note that the direction of the instantaneous velocity is always tangent to the object's path at any given point. When dealing with motion in two dimensions, it's important to separate speed and direction. Speed, or the magnitude of velocity, is given by the formula v equals the square root of v sub x squared plus v sub y squared. Since it has no direction, speed is a scalar, unlike velocity, which is a vector. To find the direction of the velocity vector, we use theta equals the inverse tangent of v sub y divided by v sub x. This gives us the angle the vector makes with the x-axis. Now, even if the magnitude of velocity or the speed stays the same, the velocity vector can still change. That's because direction can change. This concept is key in circular motion. In such cases, speed remains constant, but the velocity keeps changing due to continuous redirection of the motion. Let's look at acceleration in two dimensions. Average acceleration is defined as the change in velocity over the change in time. In component form, this becomes delta v sub x divided by delta t times I hat plus delta v sub y divided by delta t times j hat. To find the instantaneous acceleration, we take the limit as delta t approaches 0. This gives us the derivative of velocity with respect to time, a equals dv divided by dt. In components, we write a sub x equals dv sub x divided by dt, a sub y equals dv sub y divided by dt. And the vector form is a equals a sub x times I hat plus a sub y times j hat. Unlike motion in one dimension, acceleration in 2D doesn't always point in the same direction as velocity. The angle between them can vary depending on how the object moves. Let's work through a solved example of time-dependent motion. we are given a position vector r of t, which is written as r of t equals 3t times I hat plus 2t squared times j hat plus 5t times k hat. We need to find the velocity, acceleration, and the magnitude and direction at t equals 1 second. Step 1. Finding the velocity. First, we differentiate r of t with respect to time t to get the velocity vector v of t. V of t equals the derivative of r of t with respect to t, which gives us v of t equals 3 times I hat plus 4t times j hat plus 5 times k hat. Step 2. Substituting values at t equals 1 second at t equals 1 second, we substitute the value of t equals 1 into the velocity equation. V equals 3 times I hat plus 4 times j hat plus 5 times k hat. Step 3. Finding the magnitude of velocity. The magnitude of the velocity vector is found using the Pythagorean theorem. The magnitude is the square root of 3 squared plus 4 squared plus 5 squared, which is equal to the square root of 50. Step 4. Finding the acceleration. Next, we differentiate the velocity vector to get the acceleration vector of t. R of t equals the derivative of v of t with respect to t, which results in R of t equals 0 times I hat plus 4 times j hat plus 0 times k hat. So, the acceleration is constant in the y direction. Step 5. Finding the direction of the velocity vector. Finally, the direction of the velocity vector is calculated using the inverse tangent formula. Theta equals the inverse tangent of v sub y divided by v sub x. Substituting the values, we get the inverse tangent of 4 divided by 3, which equals 53 degrees from the x-axis. Let's quickly recap what we've learned about motion in a plane. We saw how vectors help us describe position, velocity, and acceleration when an object moves in 2 dimensions. We derived equations of motion in vector form and understood how each component, horizontal and vertical, can be treated independently. Real-life examples from sports, aviation, and robotics clearly show how useful this concept is. So next time you throw a frisbee or see a drone hovering sideways, you'll know it's all motion in a plane explained by physics. I hope this session gave you a clear understanding of how two-dimensional motion works using vectors. See you in the next lesson, where we'll explore projectile motion and dive even deeper.